Let's start with this function f of x equals 1 over x squared minus 4 and see if using the first and second derivative we can't get a sketch by the end of it here. Okay, so like I said, here's our original function, and so the first thing you're asked to do is get the first derivative. Now you notice that I'm not using the sheet that you're using, so you're going to want to write this down as we go so you've got it all in one place. So to find the first derivative, I just use the quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared, and that simplifies to be negative 2x over x squared minus 4 quantity squared. So that's your first derivative. Now the real fun thing is deriving that. So let's go down to the second derivative here. You can see this is what we started with. And when we take the second derivative, we do the same thing, quotient rule, bottom derivative of the top minus top derivative of the bottom, which trust me, that's the chain rule, is going to give you that derivative. And if you notice, you've got an x squared minus 4, x squared minus 4, and an x squared minus 4. Those are all exactly the same, and they're in three different spots. And by three different spots, I mean in this first term on top, the second term on top, and then the denominator. So you can cancel one out from each place, making this to the third power on the bottom, first making that go away right there, and then up here, in that first term, making it to the 1 power. So you can simplify it to be this, which is much nicer. And then you can simplify that further to be 6x squared plus 8. And if you don't believe me, do the algebra and you'll see that this is what the second derivative ends up being. Let's go on to the next thing here. So you're supposed to find the domain. The domain of this is all real numbers except for x can't be plus or minus 2 because that's where we divide by 0. And there are also asymptotes there. Alright. There are no intercepts in this one. If you try and look at the original function, set it equal to 0, you're not going to be able to find any intercepts. You will find asymptotes, vertical ones we talked about, and then there's a horizontal asymptote at y equals 0. Remember, the rule for that is that if we go back once again to the original function, the degree on top is less than the degree on the bottom, so that tells you that there's a horizontal asymptote at y equals 0. It can be super handy for graphing rational functions. Let's go on to the next one here. We're going to look at intervals of increasing and decreasing, so let me show you the work that got to the solution here. Here's my derivative. I'm going to set it equal to 0 because I know critical points happen whenever my derivative is 0 or doesn't exist. We know it doesn't exist at 2 and negative 2 because that's where the asymptotes are. So the derivative can't exist there, so that's negative 2 and 2 for critical points. When I set this equal to 0, I want you to notice that I can multiply both sides by the denominator, and I'll end up with 0 is equal to negative 2x, which is much nicer than what I started with originally. And I end up with x equals 0 as my other critical point. I go check those critical points, put it on the little number line here, and I check values like negative 3. And what I notice is that when I plug in negative 3 into my derivative here, I get a negative times a negative on top, that's a positive, divided by something squared, which is always a positive. So if you have something squared in the bottom, you know it's always positive. You don't have to plug it in and figure out what that value exactly is. Okay, so I got positive over positive gives me positive, similar here. And then once I plug in like 1, I'll get negative 2 times 1. That's a negative divided by a positive gives me a negative. Same thing with like positive 3 or 4. Alright, so what I know then is that I'm increasing from negative infinity to 0, and I'm decreasing from 0 to infinity. And I know also that I have one maximum, so you can see it all written out here, one maximum at 0, negative 1/4. I plug that 0 back into the original function to figure out exactly where that maximum is. Okay, so that's the first derivative test, intervals of increasing, decreasing. Let's look at concave up and down. So now I'm going to be dealing with my second derivative. I'll approach it the same way. When I multiply both sides by the denominator, I didn't write it out here, but you multiply both sides by the denominator, you get 0 is equal to 6x squared plus 8. When you solve that for x, you get plus or minus the square root of a negative number, which means there's no place where this function up here equals 0. Great, that means we only have to check where the second derivative doesn't exist, which is at negative 2 and 2. The process for the second derivative is just like finding the critical points. Find where it doesn't exist, find where it's 0. Alright, so then I do my little number line thing here. I'm looking at negative 2 and 2, so I'll pick like negative 3. If I plug in negative 3 up here into my original function, I'm going to have 6 times negative 3 squared, that's positive, 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 and positive on the bottom also, so I know I've got a positive number. If I plug in 0, I'm going to have positive over a negative, which is going to be negative, and positive when I plug in like positive 3. You can check if you don't believe me. So what you end up with then is plus minus plus, so concave up to the left of negative 2 and to the right of negative 2, and then concave down in the middle. There are no inflection points, and the reason for that is that even though there's a change in concavity, you and I know that these are actually asymptotes at negative 2 and 2. There's a change in concavity, but it's not an inflection point because they are vertical asymptotes at negative 2 and 2. Now, knowing all of that information, we should be able to get a sketch of the curve. So let's zoom out a little bit and see what this looks like. Over here to the left of negative 2, we know that we're increasing and concave up, and that we have there's a horizontal asymptote at 0 and at negative 2. So that bounds everything, increasing, concave up. So it must be right here. In the middle, until we get to 0, we're increasing and concave down. So that's how I know that it goes like this. I also know that I have a maximum here, right? So then to the right, I know that I'm decreasing and concave down, so that must be what that curve looks like there. And lastly, decreasing and concave up is going to give me this behavior over here, remembering that I've got the horizontal and vertical asymptotes. A major tip is graph everything you know you can put on the graph in its exact spot. Vertical asymptotes are great, horizontal asymptotes are great, maximums, minimums are great, intercepts are great if there are any. All of those solid points can really kind of lay the foundation for the rest of your function, where the curve is going to go. Remember, we're not super picky on other points, but those big points you should have drawn on the graph. And that's it for that last problem from the notes.